Right, well, welcome back to my course on potential energy surfaces and a bit of reaction dynamics from a more theoretical perspective. And today's lecture is really the culmination of all of the previous lectures. Today I hope we're going to get to where I really wanted to get to, and that is the Eyring equation. The Eyring equation essentially is a very, very simple equation, very, very similar to the Arrhenius equation, but whereas the Arrhenius equation is based purely on experimental observation, the Eyring equation can be derived exactly, and they happen to be the same, which is of course, always very nice when science agrees, theory and experiments agree. Now, in order for us to get to the Eyring equation, in order to predict the rate constant for a chemical reaction, at the end of last week, we had to go through a little bit of preliminary statistical mechanics in order to get there. Now, I've been quite open with you that the focus of any year's exam for this course, there will always be something about the Eyring equation in it. I feel that that's what the course is really all about. There'll be other things around and about it, but the Eyring equation is central to it, and nearly always a numerical example. So I will hold a workshop at the end. My last 8th lecture will focus on the numerical aspects of what we're going to talk about today. But my aim today is really to convey the concepts. Where does it come from? What does it mean? What does each term in the equation actually, where do they come from? So at the end of the last lecture, I talked about how we got an equilibrium constant. And I made things relatively simple in that I started out with two systems, A and B, but I made them isoenergetic. I had delta H is 0 here, or at least delta E is 0. I really should say delta E is 0 from the way that I presented that diagram. Now, that's no good for us because I mentioned to you again in the last lecture that one of the postulates of transition state theory is that our reactants and our transition state must be in equilibrium. In order for us to go to reaction, we've got to get to the transition state. Well, we know therefore that the reactants are not going to be the same energy as the transition state. If this here B was the transition state, then delta H would certainly not equal 0. So let us start today's lecture and let us just do exactly that. Let's think about the case when A and B are not isoenergetic. Okay, so that's A, and that is B, and that is going to be delta E. And again, each state might have a number of energy levels. And this one might have some more energy levels, differently spaced, because it's a different case. So A could be the reactants, and it's very useful to see B as being the transition state. So ultimately we'll actually join these up. So our chemical reaction, it's going to start somewhere about here, and it's going to go somewhere through here. And we recognise that we are going to have this parameter beta, which is 1 over kBt. Just want to be clear about our nomenclature, same as we've got used to before. So what is our equilibrium constant, K? Well, we can write it exactly as we have done already. Let's imagine that this system, in fact statistical mechanics will tell you that this system, with the equilibrium constant, again, it must be the same as before. It must be the ratio of the partition functions for the products and the reactants. Products over reactants, as I say, B could be transition state, A could be reactants. Now, that's all well and good, but so far, we really only consider the fact that these partition functions are vibration, rotation, and translation. If I now add in, of course I can multiply that, and I can add in now back into our thought process the electronic part. Now remember that the electronic part is the potential energy surface. It is the energy of the potential energy surface. So the fact that my blue and my blue reactants and products here are different in energies is actually reflected in the change in the electronic part. It's all to do with the actual wave function itself, the electronic wave function. So we might expect, and it will turn out to be the case, that this delta E here is going to come from our electronic part. So let's just do that. Let's expand that out and see if that happens. So again, QB over QA, which is in green. And let's expand out what those functions should be. So we should have for the partition function for the B molecule, we'll have the degeneracy, and then we'll have a sum. Of course, this should be a sum of e to the minus beta over RT or over KT. That's with our B molecule. Now really that should be a sum. This is a partition function. It should be a sum over all possible excited electronic states. But this is where we have to get real with chemistry. In chemistry, we're very lucky that most ground state reactions are moderately spaced away from their first excited states, and then the rest of the excited states are usually much higher in energy. So at the very, very worst, we usually have to consider a first excited state, but normally we only have to consider the ground state here. So we have, sorry, that should be a B, not beta. Let me just get that, make that absolute, that's EB. That's energy of the B molecule. That there is EB. Sorry, just to be clear, it's not E beta, it's EB. It's the energy of the B molecule. Only the ground state. We only need to worry about the energy of the ground state. And that will be compared to the degeneracy of the A state and the e to the minus EA over RT, or over BT, KBT. So what we've done, all I've done is I've written out the electronic part, the blue potential energy curves here, and I've expanded out the electronic part separately. And of course, if I now write that out, I can write that out in absolute full. That would be QB. Now that would be the vibrational part over QA, the vibrational part, times QB, the rotational part, over QA, the rotational part, times QB of the translational part, over QA of the translational part, times GB, the degeneracy of the B, the product, over GA. And let's just combine these E's together. That will be E, the minus delta E, over KBT. And this red part on the end all comes from the electronic part. So there are several things at work here that are going to be very, very important to the rest of the lecture. The first thing is you no need to really worry about partition functions, except for the fact that we remember that they can always be the molecular partition function is the product of vibration, rotation and translation, and that the actual relative energies of molecules appear in the electronic part of the partition function. And when I take this ratio of the electronic part of the wave part here, I end up with delta E. That's the nice feature of exponentials. And I hope now you can perhaps almost see already here a very, very useful form for this equation. The equilibrium constant tells us that if we have an endothermic reaction, then the equilibrium will be to the left. And it'll be to the left because of this electronic part, this e to the minus delta E term. If we had an exothermic reaction, then the delta E term would make the equilibrium constant favour the right-hand side. So this is what we're more familiar with. This is what we're more familiar about equilibria being to do with the relative energy of the reactants and the products. And that is emphasised in this equation here. Now, this sort of thing, I mean, you might think, this is going to be exceedingly useful to us. Why is that going to be exceedingly useful to us? Well, let us progress. Now, this is all summarised in your notes, just to be on the here. Let me just point out here. I've got a summary here from your printed notes, and I summarised the equation on the right-hand side. The equilibrium constant is, for example, here I have an equilibrium constant of the reactants are A plus B in equilibrium with C. So I can write that out and do the same sort of thing for a triatomic reaction. Now, what's different between that equation that we've just had before? You'll notice that I have divided every partition function by the volume in which our state exists. So actually, each term here, for example, that one is, or that one there, is our partition function per unit volume. And this term, and this explicit inclusion of the volume, is necessary in order to account for standard states of the chemical reactions. Equilibria, ultimately, they depend upon what is the concentration of your liquid or your solution. And that is partly taken account of by this conversion to a standard state. And we must divide each partition function and assume that our reaction is going to occur in a particular volume, or our equilibrium is within a particular volume. On my previous slide, of course, the reason it didn't show up on here, it could be there, I could have added it, but the A and B, the volume would have just cancelled. So I could have included it on here, but it would have cancelled out. When we go to a triatomic reaction, which we're going to do for the rest of the today, this volume does not cancel out. So we have to introduce it. That's an additional extra feature. And we'll see that at work as we go along. So, and of course, one thing that's going to recur again is this is actually not going to be as bad as you think. This isn't going to be a problem for us, because 2 lectures ago, or at least a lecture ago, I already introduced this the translational partition function in exactly the form we needed, per unit volume. So the fact that we need the total per unit volume, and we have a formula for the translational per unit volume, you can immediately see that we have everything we need, and there's nothing particularly difficult going to arise. Right, good. So now we're where I want to start. Let me recount what we're going to do now. We're going to go and re-look at the assumptions of transition state theory. We're going to write a formula for the rate constant for a reaction of A plus B goes to products, whatever they are, C, D, E, F, whatever it's going to be. I'm going to write down the formulae, and I'm going to discuss explicitly a bimolecular reaction, because that's the harder one. If it was a unimolecular reaction, everything would be just that bit easier, and it's not that hard to write down the bimolecular reaction. So we're going to look at a bimolecular reaction. Let's have a look at what we need to do. Where are we going to start? Well, let us start at the beginning. I want to react together A plus B, and I want to go to product C. But I've already mentioned the first assumption of transition state theory is that our reactants are going to be in equilibrium with the transition state. So this is our transition state. I'm going to represent our transition state by a double dagger. So let's give that a value. Let's give that a code. I'm going to call that Kc dagger. The equilibrium constant for the reactants going to the transition state. Well, we know then that the reaction then must continue, and it must continue to the products. let's just for now, let's just imagine the products are called C. And we know that the assumptions of transition state theory that we discussed are that the reactants and the transition state may be in equilibrium, but once we reach the transition state, we go automatically to products. So this going from the transition state to products must occur with some rate constant, K dagger. So that's going from the transition state. Once you get to the transition state, your rate of going to the products is now predefined. It has to go. And it has to go via this rate constant here. What's the overall rate of the reaction? Well, what's the overall rate? Well, the overall rate will equal the rate of formation of the products by dt. And I'm going to call that K2, that should be a 2 there. And the reason I'm using a subscript 2 is because it's a bimolecular reaction. That's the reason I put a 2 here. It's just to remind you that it's for a bimolecular reaction. And it will be defined quite simply, as everybody knows, by the product of the concentrations A and B. Well, the first thing we understand is that that is going to equal the rate at which, if we've reached the transition state, then the rate of going from the beginning to the end is all to do with going from the transition state to products, because the first part is in equilibrium, sort of steady state like. So the overall rate of the reaction can also be defined as, the rate of the reaction is defined as the rate at which we go from the transition state to the products. So it's equal to K hash times the concentration of the transition state. We can just do a bit of, let me just write a bit of, just to remind you what the Kc is equal to. Everybody can write this down. The equilibrium constant is the concentration of the products of the transition state over concentration of the reactants. I can rearrange this equation to get the concentration of the transition state which can be given by this very, very simple expression. And I can substitute that into our rate equation and discover that our rate, which is K2AB, must therefore equal this thing here, K dagger, times Kc dagger, times A times B. And I think you can now see what we can do. We can quite simply cancel out those very awkward things that theoreticians never want to actually work with, and that are concentrations. Concentrations are very much experimental. As we know, very, very important. We dictate, most of the chemistry we do is dictated by the concentrations we work in. But as a theoretician, or from a theoretical point of view, that's actually one of the most difficult aspects to work in. I like to work, and we want to work here at the atomistic level, right down at the very nitty-gritty. We're not interested in a bucket of stuff, we're interested in 1 or 2 molecules. And 1 or 2 molecules is not really very helpful if you're having to consider the concentrations. And nicely here, you learn immediately that this Eyring equation, that whole of kinetics, doesn't really depend upon concentration at this level. So, the end result is a very, very simple equation. That is that K2 is equal to K dagger, the rate constant for going from the transition state to the products, times the equilibrium constant to form those products. And this is absolutely key. This is where we really want to start. This is really where we want to start. This is our definition of the experimental rate constant in terms of 2 things that we stand a very good chance of being able to work out.
the equilibrium constant and this rate constant from the transition state. So now let us consider the next step. Has everybody got that? That's good. Didn't get any more difficult. So let me just put that up in the top corner here to remind us. Okay, let me just put that up in the top corner just to remind us of where we've got to. Let us first of all look at the very first term, this K rate constant, this rate of decomposition of the transition state. What can we say about the rate of the decomposition of the transition state? Well, a rate is so many per second. So many somethings per second. It's going to be proportional to the rate at which we cross the transition state. And this is a very, very important first step. So if I have our transition state, I can get rid of the bar, just talk about frequencies at this stage. So if we are going to go from transition state to products, then the rate at which we go to products must be proportional. If this is a classical system, it must be proportional to the frequency with which we cross the transition state. If we cross the transition state with a very high frequency, then obviously we're talking about going to products with a large rate constant. This is very, very critical. What we're doing here is we're looking at the rate constant in terms of almost a velocity, a rate of crossing the transition state. So this is the rate of crossing the transition state. So it's a frequency. Well, excellent. That's going to be quite nice. I can actually write that down slightly differently. Let me write that down as an exact equation, equals. Well, let me put something here called, I'm going to have a kappa. Try and make it into a kappa. I don't know how to, I'm going to accentuate kappa. Greek K, kappa. And this is called the transmission coefficient. So basically what I'm saying is, I know that the rate constant is proportional to this rate of crossing, but its exact formula could be really quite difficult to understand. So let's just set it equal to a constant. Some form of constant that makes that equation very, very simple. The beauty of transition state theory is that this transition statement coefficient will equal 1 from nearly every occasion that you're going to meet. For a normal chemical reaction, we assume that the rate of crossing the transition state is the rate of K dagger. So we put K equals 1. Now there are conditions where the kappa will not be 1. And this is actually where, for example, if we extend transition state theory, you can extend it into something called variational transition state theory. You can also have tunneling through potential energy barriers, which we'll cover briefly at the end next lecture. When you add in extras and you build up transition state theory into a slightly better theory, we start to mess around with kappa and we start to give it a value. We can start to modify it, maybe slightly bigger than 1. Maybe slightly less than 1. For example, if my reaction didn't always go to products, I could make my kappa less than 1 to allow some recrossing, for it to come back and forwards again. That would imply that kappa was ever so slightly less than 1. So if I want a theory that includes some backtracking before it goes forwards, I can adjust the theory and have a different value of kappa. That's very important for nearly all of your course and all your questions. Unless you're told otherwise, kappa will be 1. But it has to be included, it has to be considered. Good. Well, that's all there is at the moment to say about K dagger. Let's go to the other part now, Kc, the equilibrium constant. What can we say about the equilibrium constant? Well, the equilibrium constant is equal to what? Well, it is the products, which in this case are the transition state, over the reactants, A and QB. And because this time we definitely don't have equal energies, we're going to have the electronic part of the partition function involved. I'll include this explicitly now. This is the red part we started off the lecture with. So this is our definition of our equilibrium constant. We have to allow for the fact that it's all at standard state, so let's add in the volume factors to correct for standard states. And we have a starting point now. We have an expression for K. For the rate constant, we have an expression for the equilibrium constant. Okay. The idea of this course is just to get used to thinking about these expressions. So let's write out this K explicitly in terms of all the individual partition functions. So what have we got? So this is the total partition function for the transition state must be the rotational part of that times the translational part of that times the vibrational part of that times what's left of the electronic part of that. And we must include our volume correction. And all of that is for the transition state. What else have we got? Let's do it for molecule A. So for molecule A, we will have the rotational part of the partition function times the translational part of for A times the vibrational part of A times the electronic part of A, and we'll allow for our volume factor. And on the denominator, we have to continue. We must also have the rotational part for B, the translational part for B, the vibrational part for B, and what's left of the electronic part for B, and tag on to the end e to the minus delta E over RT. So now, are we in a position to get our to form the Eyring equation? We're almost there now. Now comes the mathematical trickery. The mathematical trickery, because we have now an expression for K, and we have an expression now for the equilibrium constant. Let's have a look at those two expressions. The expression here for the equilibrium constant is in terms of vibration or partition functions and an energy barrier. And we've got all of those numbers we can get. For any molecule, even for a transition state, we can have formulae for the rotational partition function, the translational partition function, etc. We have formulae for everything that we need in here. We also have a formula for the translational part divided by V, which doesn't include the volume. So the volume won't actually appear in that equation. But what we're still left with is this frequency here. We still haven't got a value for that. How are we going to get a value for that? And that's where I want you to consider this term here. This is the vibrational partition function for the transition state. Can we do anything with the vibrational partition function for the transition state? And the answer, you're not going to be surprised, is going to be yes. We can. Let me write out what the formula for that is. Well, the formula for a partition function I'm going to put this in terms of RT to be consistent. That is the formula for a vibrational partition function of a diatomic molecule. And it's the vibrational partition function for a diatomic molecule because I've only got one frequency in that equation. For a polyatomic molecule, which a transition state must be, I have to account for every vibrational mode in the molecule. So I have to add in this product where I is from 1 to all vibrational modes. Now, I want to consider all vibrational modes. And I need to take you back to last year, and I need to take you back to something that's on, I think, pages 8 and 9 of your notes for those who weren't here last year. And that is, if we are looking at a transition state, we'll have a barrier looking like that. It'll be an upside down well. And we know that this here is going to be our reaction coordinate. And that is our transition state. Now, one thing about a transition state is that one of the coordinates, this reaction coordinate, has what we would call an unbound vibration. All the other vibrations in the molecule, if I looked at all the other vibrations in the molecule, they would all be like that. They would be bound vibrations. E.g. in the reactant. But in a transition state, we know that one of those vibrational frequencies, one of those normal modes, is unbound. It goes the wrong way. There's only one of them, because that's what uniquely defines a transition state. And what happens, what it means is that, in fact, the vibrational frequency, if we were to calculate what that vibrational wave number would be, the vibrational wave number for this unbound vibration must be an imaginary number. E.g., nu bar for the reaction coordinate. In fact, let me write it for the reaction coordinate. There must something like equal something like 1600 I centimeters to the minus 1. So this is something that we know about the transition state, something that's unusual. One mode, one of these, all of these vibrational modes, which we're going to multiply this term by each frequency term get multiplied together. Every one of those multiplied together, but one of them is going to be a real tricky number, because one of them is going to be an imaginary number. Just one of them. All the rest will be nice, positive, normal vibrations. So what's the effect of taking out? Can we do a bit of mathematical trickery? Well, in your notes, there is, I outlined what that mathematical trickery is. And that is on top of page 47 of your main notes. You can expand this term here as a Taylor series, do a bit of mathematical rearrangement, and it will turn out that that term, where replacing just one of these terms, will become that KT upon H over nu dagger. But remember what I've done. I've taken out one of these frequencies, okay, minus the imaginary mode, the reaction coordinate. Okay, so I have taken out the term corresponding to the imaginary, to the reaction coordinate, and it becomes KT upon H all over nu bar hash. And I'll leave you as an exercise of when you're in your revision, just to clarify that you see the maths in the paper. It's not essential that you can do that bit of maths yourself, because what's important for my course is that we understand what's happening. What's happening is that the transition state has lots of vibrational energy. And the vibrational energy is partitioned, let's say, all of the vibrational modes except for the reaction coordinate, that might be 3n minus 7 coordinates, all of those have normal vibrational energy levels. So the energy is partitioned amongst those vibrational energy levels as vibrational energy. However, one of those modes is imaginary. It's an unbound vibration. And what does an unbound vibration imply? It's not bound. It's not a vibration. What is it? If it's not a vibration, then what is that motion there? What is that motion? The green motion. Anybody like to say? Okay. Well, think about it. Let's have a look. It's KT upon H term. What is it? Well, there we have, on my slide, we have a left-hand side, we have our usual contour plot to try and demonstrate the energy of a triatomic reaction. And what's happening during this first part of our reaction from our reactants through to our transition state. Okay, so this is our transition state here. The blue dot is our transition state. What's happening during that initial part of our reaction? We have relative translational energy. In fact, this part here, the reactant part, is translational energy. And what happens at the transition state? It continues to be translational energy. Relative translational energy. So what have we done? What we've actually said is that this should be a vibration. In a normal molecule, this should be a vibration. It's not a vibration. It's an unbound vibration. It still has a magnitude, but it actually corresponds to translation. It's a vibration that is actually translation. And it's translation in the sense that it's translation along the reaction coordinate. And rather than having a nasty partition function expression, this 1 over 1 minus e to the nu bar over kt vibrational partition function term, it has this very, very simple formula of kt upon h. rather than a vibration. Notice there's no vibrational wave number here. It's proportional to the temperature, which it should be for translation. This is quite a difficult concept to grasp, I think, for most people. This is not the easiest thing in the world. Okay, so let us proceed with some of our equations. So, what have we got? We have Q, a full vibrational partition function, and we have the partition function for the reaction coordinate. So for the reaction coordinate, QVIB is equal to 1 over 1 minus e to the hc nu bar over RT.
You know, for that partition function, is that supposed to be a different sign, or is that still for transition state of the vibration is?
Say it again, which parts?
Just the vibrational partition function, the first one, is that still for transition state, or because you change the sign, I don't know.
Oh, sorry, this is for the transition state as a whole. Yes? So it's a product of all possible modes. And this is what we've just done. I'm sorry, I've just recapped. I've gone back to the full one, and I've said, I'm actually doing the same thing again. Sorry if that's confused you. I'm not making progress this time. I've stepped back one step just to make sure this is clear. So that's our full vibration, of which one of these terms here corresponds to the transition state. And I mentioned that that term turns out to be h nu bar over kt to the power of 1 in the notes. See, last year, having explained it as I thought I'd explained it quite well, I'd just given you this general idea of kt upon h, I realised that in the notes it looks different, but it isn't, of course, different. That is just what we have in okay? That's what I showed you on the previous slide, and that's what's in the notes. And notice they are the same, just that it's the way that the mathematics is written out more formally in your notes than in my slides. Oops, erasing. There we go. Okay. So, the end message is, one of those terms, one of the vibrations in our transition state is actually translation. It gives this kt upon h term. But it isn't just kt upon h, it's kt upon h times the frequency. So, let's go back, repeat again. Let's go back to what we wrote before. Using the same nomenclature, let's go back to our formula, which we were looking at the equilibrium constant. And we had the rotational part for the transition state. We had the vibrational part for the transition state. We had the translational part for the transition state. And we had the electronic part of the transition state. And on the denominator, we have molecule A, and we have molecule B, and I just leave them as their full versions. So let's take a step back now. That's back to where we were, and this before we learned about this trick. So the trick was to take out of this term here, let me remove the imaginary part. Okay? So I can remove the imaginary part and put it there instead. So the bar over a partition function indicates removal of the reaction coordinate. You'll see this in my notes. I'm trying to explain the nomenclature so that when you go back to revise it today, when you try and put it all back together in your heads, you'll understand that all I've done is I've taken out part of that term there and I've replaced it here. And when I take out a bit of the term, I replace it, the bar over a partition function indicates that it's the partition function without the reaction coordinate. So similarly, Kc here, I could actually write, or I could write Kc is equal to Qr, Qv with a bar over it, Qt over V, Ge e to the minus delta E over RT, all over Qa over V, Qv over V. Okay? And that would qualify that to have a bar over it, if you prefer. This occurs in the notes in two different ways. So please don't panic if you're not. These are. I'm trying to clarify the notes because I know very few of you will get it first time through. You'll need to go back through your notes. Hopefully, this will clarify what we're trying to do. All we're trying to do is take out a bit of that, the translational part, take it out, and that leaves us with possibly all of these different nomenclature with bars over things. And when we have a bar over a partition function or a bar over an equilibrium constant, what we're actually saying is that's the equilibrium constant except for the reaction coordinate. Now let us just now put it all back together, because having done all that hard work and got our heads around all of that, we've perhaps almost forgotten why we did it. And the reason we did this is because we had this original very, very simple equation for the rate constant of the reaction, which we rewrote in terms of this proportionality with the rate of crossing the transition state. This was for the K dagger part. And we have now, for the Kc part, we can write that as Kc without the transition step, without the reaction coordinate, times ABT upon H u bar dagger. Okay, so what have we done? We've actually done very little indeed, but very significant changes. The very significant change is that by taking out the reaction coordinate and recognizing that it's translational energy, we are able here to beautifully cancel out that very unwanted term, the one that we know we were going to have a great deal of difficulty with. It cancels out the rate of crossing the transition state. And we're left with what is essentially the Eyring equation in its most simple form. And the Eyring equation is that the rate constant is equal to kappa times Kc with a bar over it for the transition state times kBt upon H. Now that is not easy. First time through. Second time through, I think you will find it's actually very easy. So your task for tomorrow is to try and go through that again. Try and go through in your own mind what we're actually trying to do. This is the equation that you really need to know. In fact, what you'll obviously need to know is that when I actually expand that, Next time I'll do it again. KC dagger, remember, is quite simply K, Q, vibration, Q, translation, Q, rotation, electronic, all over translation, vibration, translation, rotation, electronic for all for molecule A, times used for B, it's vibration, translation, rotation, times electronic for B. And then we have e to the minus delta E over k to RT on the top. And what else are we missing? Anybody tell me what we're missing? We have to eliminate from the translational vibration partition function here the kT upon h. And there we have the full, almost the full. What else are we missing? By the volumes, exactly. And there you have probably the first 10 marks in every exam question for the last 5-10 years. That equation is so important. Now obviously the next task is, can you use the formulae to get the right rate constant? And can you explain where all the different terms came from?
And I'll leave derive it.
Sorry? Will you have to derive it? Quite possibly, yes. Within the concept, within the what is in your notes. So if the stuff that's not in your notes, that's not going to be required. But within the context of your notes and what's written in your notes, yes, it is quite possible that that could be the question.